So good afternoon to all the participants. This is basically not a training program, we can say a talk show. The topic is understanding inelastic behavior of steel buildings. So obviously a difficult topic to understand, but we are fortunate enough to have Dr. Jain in this program. This is only a prelude. The next steps will be understanding the codal provisions of IS 1893, which is on earthquake. So before we understand the codal provisions, we want to know the fundamentals of earthquake. And that is why this program has been organized. It will be in series. So Dr. Jain will again deliver his presentation on IS 1893 in the month of July. He will take 2 classes simultaneously on the topic itself. So to the participants, we just want to inform that please, we have made the facility of the chat box so that the presentation goes on smoothly and there is no disturbance in between. So any questions which you find is to be placed in the chat box, which will be replied by Dr. Jain either today or in a suitable time or suitable way. Again, to the participants, we are also having a feedback form, which will be supplied to you at the end of this program, obviously for reasons which we do not want to clear it. It is known. So this feedback form is to be filled up and sent us back by your email. So this is what is for today. And we also want to inform the participants that we are going for an offline seminar in the month of July. Offline seminar in Calcutta in the month of July. The topic is use of high tensile steel in construction. Those brochures and those details will be coming on subsequently. So before we hand over to Dr. Jain, I would request our Director General, Mr. P.K. Mishra, to deliver or give an introduction to this course. Now over to Mr. Mishra.
Thank you, Mr. Ghosh. Respected Professor A.K. Jain, members from the founder steel producers and others from the steel fraternity, and dear participants, I welcome you all for this program. I also welcome Dr. T.K. Pandapadhyay. I just heard about him only a few minutes back. He was our ex-Joint Director General of INSDAG. I happily welcome you, sir. It's good to see you in this program. We are very happy that after a gap of 3 to 4 years, INSDAG has once again taken up the training programs and refresher courses on relevant topics which are of interest to the professionals of steel industry. Recently, we had a training module of about a training session of about 8 to 10 modules with Vivekananda Institute of Technology. And today, as Mr. Ghosh was telling, this is the beginning of a series of talks, and we are happy that Professor Jain is conducting this. We have decided that we will be undertaking a few training programs again on relevant topics, and a training calendar is being made, and such training calendar will be displayed in our website. Our new website is under the making. You can see that now also. Maybe within 10 to 15 days time, we'll put up a training calendar which will be of interest to all the members. We are also organizing an offline seminar. Mr. Ghosh was mentioning just now. That will be again, we are going to hold it after a very long time. We never had an offline seminar for last 3 to 4 years. And why I am telling you all this? Because the participants, the members of steel fraternity, you all need to take interest in these programs of INSDAG. And INSDAG, as you all know, is perhaps the only institute in the country which is dedicated to promotion of steel. So we look forward to your participation. We look forward to your suggestions. We look forward to your active, this thing support in conducting all these training programs and seminars. And to quote one of my founder members, the purpose of INSDAG is to make steel visible to all the users at large. So that's our objective. We are trying to make steel visible to all of you, all the users and all the professionals. I once again thank Professor Jain for his interest in this institute. And sir, we are really grateful to you and we look forward to your continued patronage in days to come. Thank you, Mr. Ghosh.
Thank you, sir. Before we hand over the proceedings for Dr. Jain, a small CV, though he is quite famous and this CV is only a formality. Professor Dr. Ashok Kumar Jain, he obtained his BSc from Meerut University in 1968, then BE Civil with honors from University of Roorkee in 1972, ME Structures with honors from University of Roorkee in 1974, PhD from University of Michigan, and Abor, USA in 1978. He is a recipient of several gold, silver, and bronze medals from the University of Roorkee. He joined University of Roorkee in September 1979 as lecturer and became professor of civil engineering in 1991 and later served as head of the department. He was director, Malviya National Institute of Technology, Jaipur from 2003 to 2006. He retired from IIT Roorkee in May 2016. So almost 44 years in IIT Roorkee from student to retirement. His main areas of interest includes multi-story buildings, towers and bridges, earthquake-resistant design of RC and steel structures. In the meantime, he has authored 5 textbooks on structures and computers: elementary structural analysis, advanced structural analysis, reinforced concrete, limit state design, dynamics of structure with MATLAB application. Dr. Jain has published over 145 papers in reputed national and international journals and conferences. He carried out pioneering work on the post-buckling inelastic response of steel braced members and concentric braced steel frames. He is a fellow of the Institute of Engineers, Indian Association of Structural Engineers, and life member of Indian Concrete Institute, Chennai, and an Indian Society of Earthquake Technology, Roorkee. Dr. Jain is also consultant to many agencies in the area of structural engineering and earthquake-resistant design. So in short, this is the background of Dr. Ashok Kumar Jain. So now I would request Professor Dr. Ashok Kumar Jain to start his deliberations. Thank you very much.
Thank you, Mr. Mishra, for those very nice words, and also Mr. Ghosh. I'm really very happy to be back in INSDAG after a gap of almost, I think, 7-8 years. Today, my lecture will be on understanding the inelastic behavior of steel buildings. These are the keywords which you will come across while I will be talking to you about it. Limit state design, steel structures, stability of elements, plastic hinge, plastic mechanisms, yielding, monotonic loading, reverse cyclic loading, hysteresis behavior, ductility, R factor, demand and capacity curves, ADR spectra, and push-pull analysis. First of all, the question arises, why do we have to use steel against reinforced concrete or against RCC? The advantages are that steel has lower weight, it is flexible to use, it has high ductility, quality control and quality assurance is much better in steel structures than in RC structures, and faster erection as well as construction. So these are the advantages. That's why we are going for steel nowadays in a very big way. I will start with this stress strain curve. You're all familiar with this stress strain curve. This for the mild steel. Up to from 0 to A, it is linear elastic. A to B is yield zone, and from B, strain hardening commences, and that is the strain hardening curve. Now, this curvilinear curve is idealized as a bilinear curve called elastoplastic curve. It is linear to the yield point, and then it becomes constant, flat. It goes up to the ultimate failure. Now, if you look at the stress strain curve, if you are carrying out the elastic design of a steel structure, or in for that matter any structure, then we only cover part of this pink zone, because Fy is the yield stress, and we don't go up to the yield stress. We apply a factor of safety on the yield stress, get the service stress. So we are able to utilize only the portion which is shown in pink color. But if you're going for the plastic design, then we also take into account the strain hardening zone, which is a very, very high zone. And this entire pink plus green zone is available to us for use in the plastic design. Plastic design leads to much more efficient steel sections as well as economy. The prerequisite, each steel member must retain its stability until collapse. That is the condition, because you want to go for the plastic design, and if any beam, any column, any flange, any web of any member or develop some kind of instability, means buckling, either it is local buckling or global buckling, then your whole efforts go as a waste. This shows the concept of energy stored and energy dissipated in a structure. The first figure shows the loading in the elastic region, and you get a carry curve under the triangular, which is shown in green color. This is the energy stored. And if you further increase the load, go into the yield zone, you also get this red zone. Now, if you start unloading, then you go back from maximum load, and from maximum deformation, you go back to the zero load. Then you find that you get this red zone as well as this yellow zone. So in the yellow zone, that is the energy recovered. And in the red zone, you find that that is the energy dissipated. And that's what you see in the fourth curve. What is the total energy dissipated in loading this specimen from 0 to the yield point, or some distance beyond yielding, and then you go to unloading. So you can see the energy dissipation, which is shown by green, is by red color here. Earlier it was only in the green color. You can see how much energy is available to you, which can be dissipated if you allow the structure to go into the inelastic zone. Stability of steel structures. There are 4 basic members: beam, column, a bracing member, and connection zone. But we are worried about the general frame stability, elastic critical buckling, lateral torsional buckling, local buckling, and restraints, especially at the plastic hinge, at the location where the plastic is expected to fall. Why stability is critical? Elastic critical buckling, lateral torsional buckling, and local buckling leads to sudden collapse. They are brittle failures. That means they collapse without any warning. No element or building can resist further load once it undergoes any kind of instability, which I mentioned just now. It means now onwards, forget about any inelastic behavior. So the point is that the design of steel structures is quite different than design of RC structures. In RC structures, we do not have this problem of stability, because those are heavy members, closed members, whereas steel, we have open members. They're lightweight, flexible, and therefore they have their own problems. So it's very important to understand the basic difference between a steel structure and an RC structure. So this local stability and the stability, all these stabilities are very critical for the performance of a steel structure, especially during severe loading like earthquake. Web and flange of a steel member may undergo local instability or global instability. You see here, these two curves. On the left side is the idealized stress strain curve, and on the right hand side is the curve for buckling stress versus effective slenderness ratio. And you find that up to a certain point, it follows the elastic buckling, and in a certain range, it goes into the inelastic buckling. Okay, this elastic buckling is known as Euler's buckling, which I think all of us are familiar. And this curve is a hyperbolic curve due to the Euler's buckling. If the stress strain curve is not bilinear, if it is curvilinear, then you still get elastic buckling and elastic buckling, and you get curvilinear curve like this. So there is a point beyond which it becomes elastic buckling depending upon the slenderness ratio of the member. Moment capacity curve versus slenderness ratio. You see here, this is the plastic moment capacity versus the slenderness ratio. And you see here, there are 4 distinct zones. One is the plastic strength, then inelastic strength, and then you have elastic strength again, which is hyperbola. Okay. And you can have 4 different categories of these sections: slender section, semi-compact section, compact section, and plastic section. So this curve is very important to understand the classification of these 4 types of sections, which is also given in IS 800 2007 code. Classification of a section. There are 4 classes which are defined in the IS 800 section 3.7 table 2. Okay. In class 1, it is plastic. And what does it mean? It means it will reach yield stress. It will also achieve plastic moment, and it will also develop plastic hinge. So yes, there are 3 parameters: reaching the yield stress level, and then developing a plastic hinge in the entire section. That means the entire section becomes yield stress in the positive and negative zone. And then it also develops a plastic hinge. It means it is able to rotate. If it is a class 2 section, it is called compact section. It will reach yield stress. It will also develop plastic moment, but it will not develop a plastic hinge. Okay. Class 3 section is a semi-compact section. Again, it will develop yield stress, but it will not develop plastic moment. It will develop semi-plastic moment. Partially it may be plastified, but it will not develop a full plastic moment. MP will not reach. Similarly, it will not have a plastic hinge. And if it is a slender member, so it is neither it will reach yield stress level, nor plastic moment, and no question of plastic hinge. So this is the very important classification of the classification of a section into these 4 classes. Okay. Stability again, the stability of beams and columns and the determination of their buckling resistance is an integral part of the design of a steel framed building. Many designers experience difficulty in evaluating the effect of many different types of end and intermediate restraints to beams and columns, and thus in determining the buckling resistance. Okay, you all have heard these terms called elastic critical force, flexure buckling resistance, and elastic critical moment. You can refer AISC code, American Code on Steel Construction, that is 360 2016 for more details. Okay, this shows lateral torsional buckling. Deformation U, that is the lateral displacement towards the midspan, and the rotation, which is shown here, which is associated with lateral torsional buckling. And this kind of buckling is very, very common in steel structures. Many people feel that this is only theoretical and this doesn't happen in practice. Well, let me tell you, this is very, very common problem with the steel structures. Many structures have collapsed because of this problem. Then another term is stiffened versus unstiffened elements. If both edges of a plate are restrained against buckling, it's called a stiffened element. The critical buckling force will be higher. You can see here in the channel section and the eye section, the valve is restrained by the flange at the top and bottom both. If only one edge is restrained against buckling, it's called unstiffened element. It will require lesser force to cause buckling. You can see an angle section. It is only restrained. The vertical lag is restrained by the horizontal lag at the top, but the bottom edge is not restrained at all. So this is called unstiffened element. Okay. So these two elements are very frequently used in steel structures, and therefore it is important to understand what is the meaning of stiffened element and unstiffened member, and what are the consequences. Then another very important issue with steel structure is the point of application of the load. This is not a very critical problem at all in RC structures, but again, this is very, very important in steel structures. The point of application of a load is critical in steel buildings. On any element, it may be applied as follows: through the center of gravity of the section, okay, through its shear center. For channel section, in the first figure, load is applied through the center of gravity and not through the shear center. In this B figure, the load is applied at the shear center, which happens to be outside the geometry of the channel section. It's very important. In the first case, you will develop what happened. Hello. In the first section, there is possibility of lateral buckling, lateral bending, whereas in the B section, torsion won't develop. Hello, oh, Mr. Ghosh, hello. So I was talking about this application of the load. It will be right through center of gravity, to the shear center, at its top flange or at its bottom flange. The load may have a stabilizing effect on the member or destabilizing effect. So it is very critical for steel structures, not for RC structures. Local buckling, open section and closed sections. Sections normally used in steel structures are I sections, channel and angle sections, which are called open sections, or rectangular and circular tubes, which are called closed sections. These sections can be regarded as a combination of individual plate elements connected together to form the required shape. The strength of compression members made of such sections depends on their slenderness ratio. For individual components of a section, slenderness ratio is defined as ratio of B upon T, that is width upon thickness. The smaller the ratio, higher the strength. That's why it is very important in steel sections like I section or channel section, etc., to check their B by T ratio. This slide shows a local buckling in the bottom flange of a I section. It's very critical. Again, what is local buckling? In beams, columns, and beam columns, under a given stress condition, at least a part of the section carries compressive stress. It may be due to axial load or it may be due to the bending moment. It will also depend upon the boundary conditions, whether it is simply supported or it is continuous or fixed ended. It may occur under strong axis bending or weak axis bending. Due to localized compression and thin and slender outstanding flange oblique web elements, B by T, localized outer plane buckling of these flange or web elements occur. This is known as local buckling, and it greatly reduces the moment or axial load carrying capacity of the beam sections. In a web, diagonal compression may develop due to shear stresses alone, and it may lead to local buckling in the web. This is how shear buckling occurs. You have a web element or a flange element, and the shear stresses are acting on the element, and the shear stresses will give rise to one diagonal tension along one of the diagonals, and along the other diagonal, it will create a axial compression. And because of the axial compression, it may buckle. You can see here flange buckling and shear buckling. So you can get a wavy curve because of the shear buckling, and the shear buckling occurs because of the presence of heavy shear stresses, which are in-plane shear stresses. The next question is, what is global buckling? Under the action of compressive stresses, the whole length of a member buckles. The compressive stress may be due to axial force or bending moment or their combination. How to deal with a huge earthquake force? You are designing a steel building subjected to a heavy earthquake force. What are your options? See, our basic problem is that we don't know what is going to be the magnitude of the earthquake at a given location, when it is going to occur, and for how long. So this unknown force, this force is totally unknown. Our problem is, as a designer, we have to, estimate this unknown force and shoot in the dark. Okay, what it means is, because there is no way we can measure the earthquake, and in India especially, we have very, very few recorded earthquakes. We may have some earthquakes that have occurred in the past, last 200 years or 300 years, but most of the earthquakes were never recorded. Even the Bhuj earthquake was not recorded. Okay, and Lateral earthquake was not recorded. Kinnaur earthquake 1975 was not recorded. So our problem is, first of all, major earthquakes in India are very few, and we don't have the data even for those earthquakes. So our problem is how to design a structure. So we have a couple of options. One is we designed to design the structure for a very, very high force. That means we make sure that our structure always remains elastic, like your Red Fort, okay, or other such monumental structures which are highly, highly over-designed, whose wall thicknesses are maybe 1 meter or more. Second option is isolate the structure from the ground, that is base isolation. Okay, it can be done. It is quite expensive, and some of you may be aware that this civil hospital in Bhuj, after this 2001 earthquake, was designed using base isolation technology. Okay, so the whole building is now resting on isolators, so that even if a magnitude 8 or 9 earthquake strikes this location, nothing will happen to the building. The hospital will remain absolutely safe. Third is you increase the damping. That is external source of damping. You know that in the steel structures we take a damping of 2% or 5%, but you can introduce artificial damping into the system, maybe 20%, maybe 30%, maybe 40%. So by introducing artificial damping into the system, you can greatly reduce the earthquake force. Again, it can be done. It's very popular nowadays and not that expensive. The fourth one is permit inelastic deformation, that is formation of the plastic hinge. Okay, this will make the structure quite economical, but I just mentioned that you have to use class 1 section, compact section, so that it will allow a plastic hinge to form, and it will not let the structure undergo local buckling or global buckling. Okay, let's try to develop an understanding of the inelastic behavior of steel buildings. Plastic hinge. Plastic hinge is very, very important. When a beam or a frame is loaded much beyond the working loads, plastic hinge may form at certain locations. On further loading, the beam or the frame, bending moments do not increase beyond the ultimate moment capacity of these sections. However, rotations at the plastic hinge keeps on increasing. Okay, this you can see very well in the lab. Okay, you can apply the load and you can see how this beam is behaving in the lab under this increasing load. A redistribution of moment takes place. The moment now being received by less stressed sections, the rotation at the plastic hinge keeps on increasing without any increase in the moment until the ultimate rotation capacity is reached, beyond which the section will collapse. Plastic hinge is a yielded zone at which an infinite rotation can take place at a constant plastic moment. Theoretically, in any beam or a column, theoretically, plastic hinge is assumed to form at the point of plastic rotation, which is shown in this figure by red color. So it is a beam or a column, you can say, and the black portion shows the beam column joint. Okay, and the plastic hinge forms at a point, theoretically, which is shown by red colors in this slide. With increase in force, the section can undergo more plastic rotation until collapse. There is a constant movement at the plastic hinge with a value equal to plastic moment capacity of the cross section. You can see here, suppose this is some joint of the any part of the structure. O is a joint, and OA, OB, OC are three members meeting at this joint. Member OA has moment inertia 2I, member OB has moment inertia 1.5I, OC has moment inertia I. And you apply a moment M at the joint O. So obviously, A will carry the maximum bending moment, B will carry less moment, C will carry the least moment because of the stiffness of these different members. So the plastic hinge, first plastic hinge will form at the end A, second will form at B, third will form at C, and so on. Elastic section, you can see a rectangular section or a I section, and you see the stress distribution. This is a triangular stress distribution, and a section happens to be symmetric. Therefore, the stress at the top and bottom fibers will be equal. So you can draw its moment rotation curve at a given section of the beam or a column. This is a partially plastic section. Partially means the flange and part of the valve have reached the yield stress as shown in this C figure. So figure section A is the rectangular section, B is I section, and C is the stress distribution which is applicable to both A as well as B. So part of the section carries yield stress, while part of the section is having linear, which is less than yield stress. So again, for this kind of section, you can develop the moment rotation curve. This is a fully plastic section. Some arbitrary shape I have shown here. So there's a neutral axis passing through the, there's a neutral axis which passes through the neutral layer of the section. Above it is, let's say, compression. Below it is tension. So the entire section has plastified. That means entire section has developed yield stress. Okay. So the force of compression must be equal to force of tension for equilibrium, and you can generate the plastic moment capacity of this section. Now, mechanism conditions is very important. I'm sure you must have read all these things in your bachelor's course or master's course somewhere. The ultimate of the collapse load is reached when a mechanism is formed. Equilibrium condition, there are three equilibrium conditions: sigma fx equal to 0, sigma fy is equal to 0, and sigma mxy is equal to 0. This is a plastic moment condition. Bending moment should not be more than the plastic moment. Now we can develop the moment curvature curve at any cross section of any member. In order to understand the plastic hinge mechanism in a given cross section, there is a need to develop its moment curvature relation considering the three conditions: elastic, elastoplastic, and plastic situation, which I just discussed with you. The moment curvature relation depends upon the geometric properties of the cross section. It is usual to plot the following relation between the following, that is m upon my versus phi upon phi y. So m is the moment, my is the yield moment, phi is the curvature, and fy is the phi y is the yield curvature. For a rectangular section, we can develop a relationship like this: m upon my is equal to this much, and this is how it looks like if you plot it. Okay, so m upon my is 1 means the yield moment, and plastic moment is 1.5 times my for a rectangular section, and you can get this curve, moment curvature curve. Now, knowing the moment curvature curve, we can generate the moment rotation curve. Ultimately, moment rotation curve is more important to us than moment curvature curve. But the problem is, in order to develop this moment rotation relationship, considering the three conditions: elastic, elastoplastic, and plastic, which we just discussed, the moment curvature rotation curve depends upon the geometric property of the cross section, span, connection type, and its detailing, torsional resistance, and boundary conditions for the span. So these are additional components which come into play if we are talking about the moment rotation curve. Okay, and this nonlinear analysis becomes very tedious and requires advanced finite element analysis modeling. Alternatively, you can carry out a full-scale experimental investigation on different types of sections and connections. It is usual to plot relation between m upon my versus theta upon theta y. Earlier, we were plotting upon phi y, which was the curvature, but now we need to plot theta versus theta upon theta y, that is the rotation. Now, minimum plastic rotation. Section 12 of IS 800 2007 plus Appendix 1, which was issued in January 2012, requires a minimum plastic rotation at the plastic edge. The different frames should be shown to withstand elastic deformation corresponding to a joint rotation of at least that shown in the table without degradation or in strength and stiffness below full yield value. So as per the IS 800, minimum plastic rotation is 0.02 radians in ordinary MRF and ordinary concentrically braced frames. And it is minimum 0.04 radians in the special MRF and special CBF, that is concentrically braced frames. Clause 12.8.2 provides geometry requirements for bracing members and connections. IS 800 is silent. How to estimate the plastic rotation? That is the worst part. See, plastic IS 800 section 12 has given these plastic rotations, but it doesn't tell how to calculate them. Now, coming to the plastic mechanisms, there are different types of plastic mechanisms possible in a steel building: beam mechanism, panel or sway mechanism, gable mechanism, joint mechanism, and a combined mechanism. This slide shows in a fixed ended beam what is a beam mechanism under a point load applied at eccentrically with the center line, and you have three locations 1, 2, and 3. The three hinges are formed in the following order as shown. First hinge will form at location number 1, second hinge will form at location number 2, and third hinge will form at location number 3 if you keep on increasing the load slowly. This shows sway mechanism, gable mechanism, and a joint mechanism. This shows combined mechanism, that is a sway mechanism and joint mechanism are combined, and at some location the hinge disappears and at some other location it may appear again. That is called combined mechanism, and these are real mechanisms and structures do fail like that. This shows regular portal frame mechanisms. A is the original portal frame having a vertical force V and a horizontal load H. And then you have three possibilities: B, C, and D. In the B, it is sway mechanism. In C, it is beam mechanism, and in D, it's a combined mechanism. Now, plastic design. Elastic design method limits the usefulness to the allowable stress of the material, which is well below the elastic limit. Remember, I just showed you that pink zone. So this is what the pink zone means here, that the elastic design method limits usefulness to the allowable stress, which is well below the elastic limit or the yield point. In plastic design, ultimate load is regarded as the design criteria. Plastic design method can be easily applied in the analysis and design of statically indeterminate framed structures. A statically indeterminate structure is able to redistribute moments from highly stressed region to less stressed region in the plastic state. Plastic design method provides a rational approach for the analysis. It is more efficient and economical. Now, types of concentrically braced steel frames. You know that there are two kinds of braced frames: concentrically braced frames and eccentrically braced frames. I had the privilege to work upon this bracing members and post-buckling behavior of course the bracing members and concentrically braced frame as well as eccentrically braced frame back in early 70s while I was studying at the University of Michigan in Ann Arbor in USA. So there are four categories of configurations: X form, diagonal brace, V inverted V or inverted V frame, and V frame. There are two other concentric configurations called diamond, which are shown here in the right hand side, and the split column K. Both these 12B figure are undesirable and they are prohibited. They are strictly prohibited. They are very dangerous. They should not be used in any building whatsoever. So you have again the same thing, a V bracing, inverted V bracing, X bracing, and diagonal bracing, and then you can use their combinations. That's how a X brace or the concentrically braced frame will collapse. Okay, here in the solid line is the original frame, and in dashed line you see the deflected shape of the concentrically braced frame. What is the effect of adding a pin-ended bracing in a moment-resistant frame? That's very clear. Let's start with the fundamentals. You have a moment-resistant frame, that's a 6-story frame, single bay. Okay, and what you do is you just add a diagonal brace in each story, having a slenderness ratio of say 120, which is a very, very slender brace. Okay, and you analyze it under lateral loads. So you analyze a MR frame under lateral load, and then you apply the same lateral load on the brace frame with having a slenderness ratio 120 say. So you will find, if you look at the forces, you will find that there's an increase in the axial force in the columns of the steel frames. Okay, there is an increase in the lateral stiffness of that brace frame. And how do you check whether there is increase or decrease in the lateral stiffness? You can monitor the lateral displacement of the roof of the frame. So in both the frames, that is MR frame and the brace frame, if you apply the same force on both the frames, you will find that the lateral displacement of the brace frame is much smaller than lateral displacement of the MR frame. Why it has happened? It has happened because by adding this very slender brace, the lateral stiffness of this frame becomes quite high, and therefore it will resist, it will give you very small lateral displacement. Alternatively, you can carry out a frequency analysis and find out what is the fundamental mode of vibration or fundamental period of vibration of both the frames, unbraced frame and braced frame. Okay, you'll find that the fundamental period of vibration of the braced frame is much smaller than that of the MR frame. So it shows that the effect of adding a pin-ended brace is that the axial force in the column increases considerably. Okay, and second thing is the stiffness increases considerably again. There are three important points in the design of a concentrically braced steel frame. First is the maximum actual design force. The design of a steel column is kept not more than about 30% of the axial force capacity. Okay, why? This is just a thumb rule, but you will find that these figures are recommended in the AIC code and other literature. If during an earthquake, there is a further increase in the axial force in a column, there is sufficient margin available in view of moment axial force interaction curve, MP interaction curve, which I'll just share with you in a minute. Okay, the brace connection is designed for the full capacity of the steel brace rather than just the design axial force based on analysis. This point number 2 is very important. See, you may get certain axial force in the brace. Normally you design for that axial force. But in case of a very severe earthquake, the steel brace may develop its full capacity. Not the design axial force, but the full capacity. This is based on this geometry. Okay, and therefore it will carry much higher axial force at collapse than what you anticipated. And that's why it is important that the brace connection should be designed for the full moment capacity, full axial force capacity of the brace, and not the design axial force. This also includes the consideration of use of any oversized bracing member over and above the design requirement. Sometimes you have a tendency that, let's say, it requires a section IS, let's say 100, but you choose to provide IS 150 for some reason. Either it is not available, or you think that may be oversafe. So against IS 100, you're providing IS 150. Okay. So by doing that, you're increasing the actual force capacity of the brace as well as the problem with the beam column joint. The beam needs to be designed so that it can resist the excessive forces and deformation in view of the collapse of the steel brace attached at its midspan. Okay. So in a CBF, a brace is designed to buckle in the event of a strong earthquake. Okay. That is the design philosophy. The design philosophy is, in a concentrically braced frame, a brace is designed to buckle. Like you have V-girder strong column frame. In a V-girder strong column frame, you are putting the girder to be weaker than the column because you want a plastic hinge should form in the beam and not in the column. Similarly, in a concentrically braced frame, the purpose of introducing a brace is that it is supposed to buckle first in the event of a severe earthquake force. That is the reason in a CBF, we keep the slenderness ratio around 120. It can also go to 150 or even 180, depending on what are the codal requirements. But we don't keep it 30, 40, or 50, or even 100. Okay? Because we want it should buckle. Why? Because we want to design a bracing member to act as a fuse, like an electric fuse. As soon as there's a higher current, the fuse will go off, and therefore it will save the main structure. Same is the principle in a concentrically braced frame. Our intention is to protect the MR frame. Okay? Our intention is to protect MR frame, that is beam columns. So if brace buckles, we don't mind, we don't care. Okay, we can always replace the brace later on with another brace. We want minimum damage to occur to the beams and columns. Okay, so it acts as a fuse and protects the MRF from the initial shock of the earthquake. Later, MRF dissipates energy by developing plastic hinge in beams. Eccentrically braced frames. You can see here two types of eccentrically braced frame. The braces are all pin connected. In the left frame, you have diagonal members. In the right frame, you have what you call as split K brace frame. The K has been split, or an inverted V has been split. Okay, so in the inverted V, you can see on the right hand side, a plastic hinge will develop in the middle of the beam at these two locations. Okay, this shows different arrangements. A is a link where plastic hinge will develop. Okay, in the B figure, the diagonal is applied such a way that A is very small as compared to B. Okay, link is a very, very small length, maybe 1/10 of the span. Okay, so these are the different arrangements that we have. These are eccentrically braced frames. Secret of the eccentrically braced steel frame. A plastic hinge develops within the link element due to unbalanced shear in the brace. So if you are using a single diagonal brace, okay, a plastic hinge will develop in the link, as I've shown here in the red color. Okay, and remember, this plastic hinge develops due to excessive shear force and not due to bending moment. Okay, normally we are tuned to develop a plastic hinge due to the bending moment. We say it is plastic moment capacity. Okay, but in this eccentrically braced frame, it's a revolutionary concept introduced by Professor Popov, E.P. Popov of the University of California, Berkeley. He worked on it in the 70s. And he came up with this idea that let us develop a plastic hinge due to shear and not due to bending moment. Okay, so you can see I've shown in this figure in the white and the green. So it develops a shear force, and then it develops a alternating shear force, and you have a shear deformation. This link element, which is part of the beam, undergoes cyclic loading due to alternative shear force and produces very fat and stable hysteresis loops. The energy distribution is remarkable. So you have two kinds of plastic hinges possible. In the left figure, the hinge forms due to shear. And in the middle portion, second figure, as you see in the figure 12.4, this hinge, plastic hinge, there are two plastic hinges that form, and these two plastic hinges form because of plastic moment. Whereas in the left figure, in the link, that hinge forms here due to shear and not due to bending moment. So it's a single hinge which forms there. The length of the link element is kept small so that it may develop cyclic shear deformations. The resulting hysteresis loop is very stable and fat. The brace is designed not to buckle in the event of a strong earthquake. Remember, in the concentrically braced frame, we designed the brace to act as a fuse. That means it is designed to buckle. Okay, and during buckling, it will dissipate energy, considerable energy, and therefore it will save the MR frame from the initially strong earthquake force, and hopefully by the time the intensity of the earthquake will go down, and the MR frame will be sufficient to resist the remaining earthquake force. But in the design of an eccentrically braced frame, our approach is different. Here we want to make sure that the brace doesn't buckle, because we want to force a plastic hinge, whether due to shear or due to bending moment, in the link. And that is possible only as long as this brace does not buckle. So the concept of designing the concentrically braced frame and eccentrically braced frame are quite different. They are opposite to each other. Okay. So brace is designed not to buckle in the event of a strong earthquake. It will force a shear hinge in the beam or plastic hinge, moment hinge in the cyclic loading. I hope this part is very clear to you, because this is not generally understood by most of the designers. But if you are going for a eccentrically braced frame, then there are very strict other additional conditions. So designing a concentrically braced frame is much easier from the point of view of quality control and design than a eccentrically braced frame. That's why even in IS 800, chapter 12, they say for design of a eccentrically braced frame, refer specialist literature. They don't discuss there how to design a eccentrically braced frame. They only discuss how to design a concentrically braced frame. Okay. Now look at the film mechanism in a moment resistant frame, MR frame. So you have a weak girder strong column in the first one. The first one is weak column strong girder, and second one is weak girder strong column. Okay, we're talking about the relative stiffness of the beams and columns. So in the first case, where the weak columns are weaker, you will develop a story mechanism or a sway mechanism, which is very, very dangerous. Okay. Second case, you develop a sway mechanism, not a story mechanism, and which is perfectly all right. Okay. So in a braced steel frame, slenderness ratio of the bracing member plays a very, very significant role. Now, let's go a little further. I hope you are all able to understand what I have discussed so far. I tried to keep my presentation as simple as possible. So, but still we have to go into the elastic region. So ductility and overstrength, that is first significant yield. When you apply a building and you subject it to a severe force, okay, maybe due to earthquake or some other reason, then the bending moment will keep on increasing, the shear force will keep on increasing, and therefore at some point in the building, first significant yield point will occur. A first significant yielding vehicle will occur, which I have shown arbitrarily somewhere in red color. And in yellow color, I am showing subsequent yield points which are not that significant initially. Okay, so that means in the first case, the red one means entire section is plastified, whereas B and this yellow color sections are partially plastified, not fully plastified. Okay, we call this red as first significant yield. This is a very, very important point in inelastic behavior of a steel building. If you plot the force deformation curve, force means the base shear and displacement means the displacement of the roof. Okay, we should be very clear about these points. Where we are calculating the force, we are calculating the base shear at the bottom of the frame and the roof displacement. And you can see this how this force deformation curve will looks like. Okay, so you can see that at a certain point this goes straight and then it becomes curvilinear. Okay, so the first significant yield where it occurred in the first this MR frame here, you can see in this figure. So the design strength is a horizontal line drawn from the first significant yield point. And all again then, if you keep on increasing the load monotonically, that means in the same direction, the frame will still go linear, and then somewhere it becomes non-linear, and it will become curvilinear. Okay, so it is red color. So as the lateral force increases with time, more passing hinges will form at various locations till collapse or withdrawal of the earthquake force. So you'll find number of locations where more passing hinges form fully or partially. You can plot all those points on this force deformation curve. And you see here, this curve, if you keep the structure elastic, totally elastic, then you go straight line right up to the top, which is the maximum elastic force. And you draw a vertical from there, that tells you what is going to be the displacement if you apply the total elastic force on the structure. Then you have the design strength corresponding to the first yield force, first significant yield, and then the location of the other passing hinges that form on the structure. And the ratio of the actual strength to the design strength is called over strength in the building. Okay, actual strength is the nonlinear curve that you get, force deformation curve where all the passing hinges are plotted on the force deformation curve. So the ratio of the actual strength to the design strength is called over strength. And R is equal to 1 is called elastic. I will tell you what is R factor. Now, equal displacement concept of the elastic design. Now, this is a very, very important concept in the design of a elastic design of a structure. Okay, you get this force deformation curve, force on the vertical axis, deformation on the horizontal axis. Force, as I said, is the base shear, and displacement is the roof displacement. Okay, so if you plot this force deformation curve, you get a straight line up to the elastic, and you get corresponding design displacement. What you can do is you can define some point as design force, and from there you take the structure into the inelastic region, so that the design displacement in the elastic design and inelastic design is equal. So what was observed, that in a building you design it building to remain fully elastic, and by carrying out number of iterations, you can design the building to become significantly plastic, whereas the total displacement of the elastic design and inelastic design are almost equal. Okay, this gives a lot of confidence to the designers that let us keep the design displacement equal to the elastic design, but don't design a structure elastically, but design it inelastically, so that you get a lot of economy. Okay, you want the section should be efficient, it should be economical. At the same time, you can get the design displacement equal in the elastic design as well as in elastic design. This is possible. A lot of work has been done, and it's all published. Okay, now here in this curve, what I am showing here in this figure is that controlling parameter is the equal displacement in the elastic and inelastic regions. I have shown two elastic force levels, force F2, which is the highest value here, which goes up to this end of this yellow curve, delta 2, F2 and delta 2, and then elastic force F1, which is F1 delta 1. And delta Y is the yield displacement up to the linear range. Okay, so you have an option. You can design it, the same structure, either to remain in the pink zone, that is corresponding to F1 delta 1, or corresponding to yellow zone, that is F2 delta 2. Okay, what is ductility? Ductility is ratio of maximum displacement to the yield displacement without any instability and collapse of the structure. Okay, so delta Y is known to you. So the ratio of delta 2 upon delta Y is ductility. Okay, or the ratio of delta 1 to delta Y is ductility. Okay, so if you are going for ductility corresponding to delta 2, so you want so much region to become elastic, you have to pay the price. As designer, you have to make more efforts in the building to make sure that delta 2 displacement is reachable, it is achievable. Okay, for that you have to make sure that the structure remains stable, no local buckling or global buckling anywhere in the structure. Type of loading on the building. See, loading can be force controlled or displacement control. I'm talking about the lab, in the lab. Okay, you can load a building in the lab either by controlling the force. That means you tell your machine that you want to apply a load of 100 tons at the building at different locations. Okay, or you can make it displacement control. You can say that I want roof should be displaced by an amount 5 centimeters. And whatever force is required to be applied to generate a displacement of 5 centimeter, you apply. So the machine will automatically calculate, depending upon the strength and stiffness of the building, corresponding to a displacement of 50 millimeter, how much load it has to generate. And it will generate that load and apply. So it will show you, it will push the building so that at the desired point, at the control point, you will have a displacement of 5 centimeters. If we say further, apply more displacement so that it becomes 75 millimeter, again, it will calculate automatically, depending upon the strength and stiffness of the building, how much more load I have to apply, and it will apply so that you get a displacement of 75 millimeter. Remember, force controlled machines are available very cheap, and all labs have those machines. But displacement control machines are very, very expensive. They run into crores. So only very selected institutes or labs anywhere in any country can afford those machines. Their maintenance, AMC, is very costly. And of course, you have to be very careful in using those machines. They're very sensitive. So you can apply the load monotonically, that means the same direction, or the reversed cyclic load, depending upon what's your aim, what do you want to study. Under monotonic load, you get these kind of force deformation relationship. The first figure, it is a brittle behavior under force control. Okay. The second figure, it is ductile behavior, but force control. Ductile means you have elastic curve. Linear is, first linear and then a flat curve, which is idealized curve, of course. So this is called ductile behavior. It is again a force controlled behavior. The third figure, you further increase the force so that there's a drop in the force at certain displacement, and then again there is a additional displacement. So this drop in the force, where we get negative stiffness or zero stiffness of the building, this part can be captured only by a machine which is monitored displacement control, not force control. Okay. If you're using a force control, you can get either behavior A or behavior B. Okay. But you cannot get behavior C if you are using a force control machine. Okay. So to get behavior C, that means what happens post yielding. Okay. how the structure will behave post-yielding, how it will develop a zero stiffness or a negative stiffness and further deformations. This part you can develop only under displacement control machine. This is the moment rotation curve. You have moment on the y-axis and rotation on the x-axis. You have A, B, C, D, E. I just mentioned to you, this is the post-buckling behavior, post-yielding behavior at A, B, C, D, E. Okay. And B is My and C is Mu or the MP, plastic moment capacity, which can be 1.1 times My or 1.5 times My, depending upon what is the geometry of the section that you are using for this particular case. Okay, from B onwards, this rotation is called plastic rotation theta P, and the rotation up to point E is 1.5 to 2 times theta P. Okay, that is the concept of ductility, and that's what you expect in case of a steel structure if you want to push it to the ductile limit. Acceptance criteria is a term called acceptance criteria. Moment on the y-axis and rotation on the x-axis, A, B, C, D, E. Then I've also shown here 3 more terms called IO. It's called immediate occupancy. LS is life safety, and CP is collapse prevention. Okay. These are called performance states for the primary element or the main elements. IO, LS, CP. What is IO? IO means immediately after the earthquake has occurred, the structure is fully capable of being occupied again. Okay, so you can, the degree of damage is very, very small. So whatever damage is there, there's very minor damage, if at all there's any. And this is called immediate occupancy. That means after the earthquake, the building can be occupied immediately. All the people who are working in the building earlier can come back and start using as if nothing has happened. Okay, so that means the degree of damage in IO is almost 0. LS is called life safety. It is a life safety situation. The life is safe, but the damage is quite significant. It's as much as 75% of the collapse prevention. CP is what we call collapse prevention. That means the building can undergo very, very severe damage, but the frame should remain standing. The MR frame or the Brazed frame must not come down. Okay, because if it comes down, then all the people who are stuck in the building, their lives will be lost. Okay, we want that those people who are inside those buildings we should be able to take them out safely. Okay, because life is the most important parameter at that time. Okay, we don't care about the damage to the building. Let the building be totally damaged. We don't care. We may have to demolish it. Fine, no problem. But we have to save the lives at any cost. Okay, so collapse prevention means depending upon the loss of lateral forces to capacity, but the structure should not collapse. Okay, I hope these performance states are acceptable to you, are understood by you, and these are the acceptable performance states for a building nowadays. The secondary elements, again, same parameters which are shown there. Under reverse cyclic loading, what happens if you apply a building under the reversed cyclic loading? Okay, characteristics of the hysteresis behavior. You will find because of the repeated and the reversed cyclic loading, there is a reduction in the strength, the cyclic loading. There is a reduction in the stiffness of the structure with cyclic loading. Or there may be a combination of reduction in the strength as well as reduction in the stiffness of the building. Okay, they can go simultaneously. So this again based on the concept of ductility, and you will find that there can be several combinations. Okay, so this curve that you see here in a dark color called backbone curve. This is a realistic curve, a real curve obtained from the lab on some beam. Okay, and what you see is the different loops where they keep rotating, means they're losing their stiffness. The slope of each line shows the stiffness, and the maximum level at the top shows the loss in strength. So you see here continuously loss in strength as well as loss in stiffness simultaneously. Okay. And this whole loop, one cyclic loop, is called hysteresis loop or hysteresis behavior. Okay. Normally, these eccentrically braced frames will exhibit the hysteresis behavior shown on the left side. Tactile hysteresis loops. This is the loop that is very fat, and the area under each curve uses the energy dissipation during the cyclic loading by that steel frame. And as far as the right hand side is concerned, this kind of hysteresis loop you get in case of a concentrically braced frame. Okay, so you can see here that a concentrically braced frame energy dissipation is very small as compared to that on the eccentrically braced frame. Okay, so we want to go for an eccentrically braced frame, but as a designer, there's a very huge penalty, you can say, or the cost involved for designing a eccentrically braced frame to get a curve like this. Okay, so you have to have a trade-off between the behavior steel and the cost. Which one do you want? Do you want left kind of behavior or the right kind of behavior? Okay, so it will depend upon the travel structure and other things. Factors affecting the deterioration of the building: material properties, initial imperfections of geometry and eccentricity of loading, magnitude and distribution of the residual stresses. Residuals are very, very important in steel structures, whether due to welding or due to some other reasons. Type and position of the loads, location type of restraint at ends and intermediate locations, and type of connections. Again, source of deterioration, compression flange throughout the length of the beam must be adequately restrained against lateral torsional buckling, local buckling, and global buckling. Okay. Modeling of deterioration is a complex issue. It's a very complex issue. In most practical cases, reliance must be placed on experimental evidence. Large number of experiments have been done, hundreds of thousands, in the Western countries, mostly in America, Japan, and England, on these steel structures. Simplifications must be made. It is a matter of engineering judgment to decide when a source of deterioration is sufficiently important contributor to response and must be incorporated in the analytical design. Now, if you are using Etabs, in the Etabs, when you go to the design module, you can specify lateral bracing. Okay, lateral restraints can be specified. Okay, and there are two types of options available in Etabs for design of a steel structure. One is the specify point bracing or specify uniform bracing. Okay, and if you further go into the point bracing or the uniform bracing, you go inside it, then there are three more options that you get. Whether you want to apply this bracing or the lateral restraint to the compression flange at the top flange or the bottom flange or throughout. Okay, it will see, this will be important if you're designing a simple supported beam. In a simple supported beam, top flange is only under compression and bottom flange is always under tension. So you can say in that case, you want to apply the lateral restraint at the top flange. Okay, but if you're designing a fixed ended beam, then near the supports where you have hogging bending moment, there the top is under tension and the bottom flange is under compression. Okay, and in the central portion between the point of inflections, the top is under compression, the bottom is under tension. Okay, so here you can specify along the length of that fixed ended member or a continuous beam in which zone the compression is occurring, whether it's the bottom flange or the top flange, and accordingly you can specify in Etabs where you want to apply the lateral restraints. Okay. We'll also refer AISC code 360 for member stability bracing appendix 6. It's very important. Now, capacity design is again a very, very important parameter in capacity design, and it is quite, catching up nowadays, both for RC design as well as steel design. What it means? It means the location of a plastic hinge is predetermined and guaranteed at certain locations. That means, see, otherwise in a building, you can say hinge will develop at the end of the beams or at the end of the column. Okay, but where it will exactly where it will occur, it is very difficult to predict. But by making use of the capacity design, you can guarantee that hinge will form at this location only and not anywhere else in this region. Okay, how do you do that? Suppose you want in this frame, you want a hinge to form at that location which I have shown by MP. Okay, so in this beam column joint, there are 4 members are meeting. So what you will do, you will calculate what is the maximum force developed in these 3 members where you don't want passage to form. So what you will do is locally you will design these 2 columns, upper column and the lower column, and the right beam for a much higher force than you are getting as per your calculations. Okay, so they may be designed maybe 25% higher force. So when you design those 3 members for a 25% higher force than what is calculated by your various combinations, then obviously, and you don't touch the design of this left beam. This beam will be designed as per the original force. Okay, so that means this is the weaker section as compared to the other 3 locations. Therefore, plastic hinge will form at this location only. It cannot form in the top of the upper column or lower column or on the right beam. Okay, that is the meaning of the capacity design. You increase the force in the adjoining areas by a certain parameter so that hinge will form only at the desired location, not anywhere else. Non-linear analysis. A non-linear analysis is very sensitive to modeling of the structure and the various metal properties assigned to the beams, columns, shear walls, braces, and joints, etc. The interpretation of a result is again a very, very tricky feature. Okay, my advice to you is please do not carry out this plastic analysis and non-analysis of steel frames or even RC frames if you don't have sufficient proper training. It should be done only by a person who has thorough experience in this kind of analysis. Otherwise, you will make blunders. The strength and the stiffness, degradation with cyclic loads, and hysteresis models, they are very, very sensitive and they can give you totally misleading results. Okay. Nowadays, people think that they are having Etabs or STAD or some other software with their pocket, and therefore they just ask from somewhere, how to proceed the data, how to carry out the analysis, and they say, oh yeah, I got these curves and I know my ductility is so much and so on. Okay, those are highly misleading, highly problematic. Please be careful. Demand versus capacity. Again, this is a very, very important parameter. You have to be very, very careful with this term, demand and capacity. Analytical nonlinear seismic studies on a computer, no matter how sophisticated the model is, it will always give you what you call as seismic demand or ductility demand for each lateral load resisting element in the building for the given earthquake input. So whatever ductility you get, whatever ductility your software shows you, whether it is Etabs or STAD or some other, there are very large number of commercial softwares available nowadays. They're very sophisticated. They are available in the market, but they will all give you ductility demand, not ductility capacity. Okay. Now, the $1 million question is how to find the seismic capacity or ductility capacity for each lateral load resisting element in the building for a given input parameter. Okay. This can only be done by carrying out a full-scale displacement control testing of the entire building in field conditions, not in the lab environment. See, when you're carrying out a computer analysis, in computer analysis, everything is idealized. You don't know what are the workmanship flaws. You don't know where the certain members are overstressed or understressed, and so on and so forth. Where there are other problems in the welding, where the welding defects, and so on. Where you have provided lateral restraints, where you have not provided adequate lateral restraints. Okay, those things your computer model cannot detect. Therefore, capacity means what is the actual capacity of the building. Forget about the loads. Now you remove all the loads. Okay, remove your computer models. Now we are talking about a real building which is standing in the field. Okay, so that real building which is standing in the real field, how do you know what is the capacity of it? Okay, and the only way to determine the capacity is carrying out a full-scale displacement control testing of the entire building, the field conditions, not even in the lab environment. The main challenge in determining the seismic capacity is the modeling of the construction defects or source of deterioration in the material and elements. Okay, these parameters vary with each construction site and manpower of the day. Today you have got very good technicians, very good labor, you get very good quality. Tomorrow, you get some untrained people, and they can ruin the whole thing. They can ruin the whole party, and you may never know it till that occurs. The author is not sure if any tests have been done anywhere in India to estimate the seismic capacity of any lateral load resisting element. Okay, whether it is a beam, whether it is a column, I'm not aware of any test done either in any IIT or any other lab, SCRC or others. How far can we rely on foreign tests and their workmanship and their site controls is open to questions. Okay, our codes are based on copy, paste, and edit technology. We copy something from Eurocode, something from AIC code or Australian code, and put it in our steel code or any other code. Okay, but those are the data based on those foreign countries, foreign sections, and their workmanship and lab control conditions, not in our conditions. Okay. Modified stiffness. Accentuated by resonant stresses in members can produce a general softening of the structure at the strength limit state that further creates additional destabilizing effects. The direct analysis method is also called calibrated against inelastic distributed plasticity analysis that account for the spread of plasticity through the member cross section and along the member length. AIC 360 further requires that reduced flexion and reduced axial stiffness should be used for inelastic analysis. It says EI should be taken as 0.8 RB tau B times EI and AE, that is axial stiffness, 0.8 tau B AE. The factor tau B is similar to the elastic stiffness reduction factor implied in the column curve to account for loss of stiffness under high compression loads. Increase local redundancy by designing hinge sequences. This is again concept of ductility. You get this force deformation curve showing different hinges. Red color is the first significant yield, and then other hinges will fall on this force deformation curve. We want a curve like this up to the failure, up to the desired ductility level. Okay. Now, what is R? R is the reduction factor that you apply to the elastic force to get the design strength. Okay, the factor different R factors on strength and displacement. Lower the design strength, higher the ductility demand. So you want a higher reduction factor. That means you want to reduce the design strength. Fine, you can reduce the design strength, but by a significant reduction in the design strength, you get correspondingly higher displacement, higher yield displacement, higher total displacement. Okay. To get a higher total displacement, that means higher ductility demand. You have to make extra efforts in the building. Okay, so the purpose of R is to reduce elastic force. If you want to keep your design simple, keep R is equal to 1. That means you design the structure for elastic force so that the building remains always elastic no matter what is the magnitude of earthquake force. Okay, and that will make your structure very, very heavy, very, very bulky. Okay, so what you do is, instead of going for that option, making the cost very, very high, you reduce the cost by using some appropriate R factor. And R factor will depend upon the structural system that you adopted. So you have to select what are the different structural systems possible at a given site. And with a given structural system, what is the maximum R that you can use easily, which you can easily construct, and that will meet most of your parameters. Okay. What is factor R? IS 18931 defines it as a response reduction factor. It means it is used to reduce the elastic response to inelastic response. Okay. The extent of elasticity depends upon the choice of factor R. Higher the factor R, higher is the level of elasticity. Okay. Higher the factor R, higher is the level of elasticity. However, in each code, it is a combination of several factors, some explicit, some implicit. Each code means each code of the same country, that is concrete code or steel code or earthquake code, and so code on water tanks, code on industrial buildings, and Indian code and American code, or the European code or Japanese code or the Australian code. So each code is different. R by definition is, as I mentioned here, it is a factor to reduce the elastic response to elastic response, but it is a combination of many other factors. Some are explicitly known to you, others are not known to you. They are based on experience and judgment. Okay. In the Indian code, it is also used to calibrate the base shear due to earthquake in IS 193 Part 1 1984 code. Okay. And IS 193 Part 1 2002 code oblique 2016 code. Okay. The R factor was introduced in the 2002 code, Part 1. So at that time, our intention was that whatever earthquake force you are getting in a zone 1 and zone 4 or zone 5, in a ductile building and a non-ductile building, because earlier the factor was totally different. See here, base shear as per IS 1893. In the 1984 code, if you recall, the base shear was given by the factor VB is equal to alpha H W delta. Delta is the damping factor. Okay, so in the 84 code, the formula for alpha H was beta I F0 SA by G. Okay, beta was the swell foundation factor, I was the importance factor, F0 was the zone factor, and SA by G was the spectral accelerations. Okay. Now in the 193 Part 1 2002 code, the formula for alpha H was totally different. It was Z by 2 into I by R into S upon G. Okay. So now this formula in the 84 code is quite different than that given in 2002 code. Okay. So once you are having a two totally different formulas from two totally different sources, how do you assign the values to various factors so that alpha H is same or nearly same as you got from the 84 code? Okay. So what is important here is that if you're designing a building in 2002 or 2003, which is started in let's say 2001 and completed in 2010. Okay. Now, if you're designing at alpha H corresponding to 84 code, and suddenly you say that the building is half built, the foundation has been built, lower 3 stories have been built, and now you say that the code has been revised. Now you revise the design of this building according to 2002 code, which gives you alpha H, which is 2 times the alpha H computed by 84 code. Now, who will be able to design this building? Can you strengthen the building by that much factor? The answer is no. And what will happen to the owner? It has already sunk so much money in it. Your building is designed using 84 code, and in the middle of the building, when it is under construction or just completed, the base shear becomes 50% higher or 100% higher. What do? Everybody is stuck then. So you can't put the designers into a situation like this. Therefore, it is important that the alpha H obtained from this 2002 code should be more or less the same as in the 84 code. That's called calibration of the codes. The base shear has to be calibrated in both the methods so that the base shear is nearly same, so that nobody is put to any kind of inconvenience and a awkward situation. Okay. Now you can calculate R factor by carrying out nonlinear analysis. This figure I have shown here, R factor actually is a function of the time period of the structure, and also ductility factor, ductility. How much ductility you want. So corresponding to a given ductility, the actual R factor is not a constant value. It varies as shown in this curve. This is based on a hysteresis model using stiffness degrading hysteresis model for 5% damping. Okay, the ductility ratio was changed from 1.5 to 8. Okay, this research was done by my two graduate students, Mr. Paul and Zasaga, in 1985, and this paper was published in 87. So a nonlinear analysis can be done on a single equilibrium system to derive the R factor for a given earthquake and given hysteresis model. Okay, you have R factor varying from 0 to 8, and this is how the R factor looks like. Of course, the R factor given in the code are much more simplified than this, but it is possible to calculate actual R factor for a given hysteresis model for a given structural system, and you can calculate what is the value of R for a given time period of the building. The value of the various parameters in this equation for horizontal seismic coefficient were developed based on experience and judgment as given in the 2002 code. The governing criteria was that the base shear determined using the 9384 code and 2002 edition must nearly match in all zones and for various time periods. Okay, so 193 2002 code was calibrated with respect to 84 edition for base shear, and R factors given in the code, whether it is 2016 code or 2002 code or even your IRC 6 code for bridges, those are based on pure judgment and experience. Classification of sections for ductility in AIRC 341 2016 code. It has two categories of the ductility classifications based on ductility: moderately ductile members and highly ductile members. And it depends on the width of thickness ratio, refer table D1.1. AISC 341. Chapter 12 of IS 800 versus AISC 341. Most designers are quite unhappy with Chapter 12 of IS 800 covering the seismic design of the steel frames. So AIS 341, seismic provisions for structural steel building, is very comprehensive and user-friendly code. Okay, and AISC 7 on minimum design loads must also be used as a companion in order to design a building using AISC 341 code. Moment frame systems, AISC 341 2016. I will take another five minutes. I hope it's okay with all of you. Okay, I hope I'm not giving a very strong dose to you. I'll just take another 5-10 minutes to finish it.
Okay, sir. Okay.
So moment frame systems, as given in the AISC 341, they have defined these 6 types of frames: E1, E2, E3, E4, E5, E6. Ordinary moment frames, intermediate moment frames, special moment frames, special truss moment frames, ordinary cantilever column systems, and special cantilever column systems. Beam to column connections requirement. Issue ordinary frame, or the intermediate frame, and special frame. The story drift angle in ordinary frame or intermediate frame is 0.02 radians, whereas in special frame it is 0.04 radians. Flux and resistance determined at the column face, 0.8 MP of the connected beam at 0.02 radian story drift, and 0.8 MPa of the connected beam at 0.04 radian story drift. Okay. Now AISC 341 2016 code refers to AISC 7 for story drift calculations. That means how to calculate this story drift of 0.02 radians and 0.04 radians. Remember, IS 800 chapter 12 also gives the same numbers 0.02 radians and 0.04 radians. It says plastic rotation. It uses the term plastic rotation and doesn't tell you how to calculate. Okay. In the AIC code, they call it story drift angle of 0.02 radians and 0.04 radians. Okay. That's what I'm saying. In our Indian code, we have a very bad habit of copy, paste, and edit technology. Come from somewhere, you paste it, and then make some changes to look like as if it is your original invention, which is extremely dangerous. And this is, we have ruined most of our steel structure codes, not only steel, but RC code also, because of this tendency. Okay. So in AISC, 341 refers to AISC 7 for story drift calculations of 0.02 radians and 0.04 radians. In brazed steel frame systems, there are 5 types of frames: ordinary concentrically brazed frames, special concentrically brazed frames, eccentrically brazed frames, buckling resistant brazed frames, special plate shear walls. In ordinary concentric frames, they permit only V and inverted V brace only, no other combination. Okay. Beam to column connections, the connection shall be a simple connection where the required rotation is 0.025 radius. Okay. In ASC 7 plus 12.8.6 specifies how to estimate the story drift index. It is given by this formula: delta is equal to CD, delta 2 minus delta 1 upon IE, and delta 2, delta 1, IE, etc. are defined in this figure. So please note down this reference: ASC 7 plus 12.86. Okay. Now, axial force moment interaction curve for a column is very important. This shows the compression axial force on the y-axis and bending moment on the x-axis. Okay, and that's how the MP interaction curve looks like. So if your force is axial force in a column is very high, which is, let's say, shown by the blue curve. So you, from blue curve, from axial force, you draw a horizontal line and you intersect the envelope and then draw a vertical. And it tells you, the vertical tells you what is the moment carrying capacity of this column. Okay, so if the axial force is very high, the moment carrying capacity becomes very, very small. On the other hand, if you apply the design force shown by the red color, axial force, so again you draw a horizontal curve from the axial force and intersect the envelope curve, and from there you draw a vertical. Now there it tells you what is the moment carrying capacity. So you find here that corresponding to the red force, the moment carrying capacity is quite high as compared to that given by the blue curve. Okay. Alternatively, you can go for the green curve, where the axial force is very, very small, but then the moment carrying capacity is very high, which is equal to MP, the positive moment capacity of the section. So what I'm saying is that the axial force moment interaction curve for a steel column is very crucial. So you don't want to design axial force in a column to be very high. That's the reason, if you remember, I mentioned in the beginning that we try to keep the axial force in a column, the steel column, around 30% or 40% of the axial force capacity of this column. Okay, so the maximum axial force is only 40%, so that in case of an earthquake, if the axial force is increasing, you still have sufficient moment capacity available to you to resist that earthquake force. If you exhaust in the initial design only the entire moment carrying capacity, then your building is going to surely collapse or not likely to survive a strong earthquake. Okay, so please remember that's axial force capacity. We don't want to keep the axial force to more than 30% to 40% of a steel column. We leave that margin in case of earthquake because we don't know what is going to be the magnitude of the earthquake. We don't know how much ductility it can achieve. What is the ductility demand what is the ductility capacity? We don't know those parameters exactly. Approximately we do, but not exactly. So we keep some factor of safety in our pocket so that our buildings don't collapse. People don't die unnecessarily. We greater strong column proportions. Column shall be designed using the load combination, including the amplified seismic load. The required axial strength shall not exceed 15% or 30% in certain cases of the available axial strength for these load combinations only. This is what is specified in the literature on American steel buildings. And the moment carrying capacity is of the MC, that is some of the moment carrying capacity of the columns meeting at a joint, should be 20% higher than the moment carrying capacity of the beams at that joint. Okay. And this is to be satisfied in both the vertical planes along the x-axis and along the y-axis in plan. Some people say that this condition is very stringent. It makes the design of the column very uneconomical. Columns are become very hefty, but we have no option. Sorry. This condition has to be satisfied. Then we want a strong column and let them increase by whatever they have to increase. Pushover analysis. Nowadays, because softwares are available to you, whether Etabs or STAD or some other software, and they have built-in pushover options available there, I find a lot of people, even fresh graduates or fresh designers, hardly having 1 year experience, 2 years experience, they love to carry out pushover analysis and feel very excited, very happy that, look, I've designed a building which survives all these things. But I doubt very much if they understand what is the meaning of pushover analysis and how to carry it out. Okay. Just because you have a software available to you doesn't mean you know how to use it or how to interpret it. Caution. Such analysis only provide a reasonable estimate of ductility demand on a building. However, it gives an estimate of ductility capacity based on certain assumptions which may not be true in Indian conditions because of the workmanship and QA/QC at the site. The interpretation of results could be a very, very tedious task. Okay. You have to refer ASC 41, FEMA 356, FEMA 440, ATC 40, and other literature. See, this tells you a schematic representation of a pushover analysis. On the left side, you have full multi-story building. So what you do, first of all, in a pushover analysis, see, I'm just trying to tell you what is the concept behind pushover analysis. Because most people don't understand what is the concept behind pushover analysis, and they just started using it because it is available in the softwares which they are using, and they attend some lecture like my lecture like this, because everybody is nowadays conducting pushover analysis lectures for the last year or two. And many people have attended those lectures, and they think that now, since we have attended a lecture, we are capable of running this pushover analysis without understanding the fundamentals of pushover analysis. So what you do here actually in a pushover analysis, you have a multi-story building which is a 3-dimensional space frame. You convert this into a single degree freedom system, a single degree freedom oscillator, like I have shown in the middle figure. Okay, and then you take the single degree freedom system as subject to a given earthquake force or given lateral force, and you calculate what is the force deformation behavior, and you calculate the ADRS spectra. Okay, ADRS means acceleration, displacement, response spectra. Okay, so you get force deformation curve, you get spectral period spectra, and then from there you plot this ADRS spectra. ADRS spectra means you plot acceleration on the y-axis, displacement on the x-axis, and you get certain spectra. You get two kinds of spectra. One is called demand spectra, other is called capacity spectra. Okay, and wherever they intersect, that's called performance point. Okay, And the displacement up to the performance point is called target displacement. You specify a certain location in the building that this is your target displacement, this is your point of interest, and there so much displacement should be achieved during this push over analysis. So once you get this performance point or the target displacement, you again, remember, you again interpret these results back to that for a multi-degree freedom system. Because your original building was a multi-degree freedom system, not a single degree freedom system. Okay. So what you did, you simplified it to a single degree freedom system, carry out your push-over analysis. Final results have to be interpreted back for the multi-degree freedom system, the three-dimensional space frame, not for single degree freedom system that you had only simplified it temporarily. You can imagine how much approximation is involved, how many assumptions are involved in this entire process, how complicated it is. Okay. I can tell you that this is still in the development stage. It is not the last word on the push-over analysis. Now, how to define plastic hinge in Etabs? Etabs gives an option to define a plastic hinge in each member, steel or RCC, beam or column or wall, by the user or by using auto hinge option. The auto hinge option is based on the experimental data compiled in the USA on very large number of steel sections, beams and columns, and RC sections, again, beams and columns. Okay. There is no such data ever generated for the Indian sections under the Indian workmanship and QA/QC at the Indian sites, to the best of my knowledge. Okay. So what we are doing is we are using the data generated by Americans in their labs for their sections, for their requirements, and we are copying that for our conditions, which I find very, very unbelievable. In beams, we want to introduce moment hinges. In columns, we are introducing P, M3, M2 hinges. Then axial force, moment about weak axis, moment about strong axis hinge. If you see in your Etabs, you go to the auto hinge option, because most people use auto hinge option because they find it easiest based on ASC 41 booklet. Okay, there, in the Etabs, you find they're saying that we will be using this auto hinge option based on ASC 41 given in table 9.6, 9.6, 9.7 for steel beams, steel columns, and steel braces. Similarly, for concrete columns, they say we'll be using table 10. So they are using the auto hinge option based on the information generated and presented in table 9, table 10 of ASC 41 publication, which are based on exclusively on sections which are American sections, not Indian sections. Okay. And Indian people are carrying out, our friends are carrying out this push-over analysis using ASC 41. Now, what is target displacement? The inelastic response of the multi-degree freedom system is estimated through the inelastic response of single degree freedom system obtained statically. Currently, there are two options for carrying out push-over analysis. One is the equivalent linearization method called EL, and other is the displacement modification method DM. Both the demand spectrum and the capacity spectrum of the SDF system are plotted in the ADRS format. The interaction of these two curves is referred to as the performance point as shown in the same table. Next slide. Okay, the corresponding displacement is referred to as the target displacement. It is presumed that the target displacement would be the actual displacement obtained if multi-degree system was subjected to non-linear analysis in a real earthquake. This line is very, very important. I will repeat. It is presumed that the target displacement would be actual displacement obtained if the multi-degree freedom space frame was subjected to the nonlinear analysis in the real earthquake. Okay, I just plotted here IS-193 spectra in the ADRS format. That's how it will look like. You are all familiar with this 193 spectra, response spectra given in the 193 2016 code. Okay, but you plot the same code, same spectra in the ADRS format, how it look like. That's how it will look like. Okay, here is the target displacement. You have the demand spectra shown in the red color, you have the capacity spectra shown in the blue color, and wherever they intersect, that's called performance point. I just also discussed this just a few minutes earlier. Okay, the displacement corresponding to this performance point is called target displacement in. Now, what is the problem? The problem is locating the performance point. The location of the performance point again depends upon the assumptions made in the procedure based on the American code. 1893 part is quite different conceptually than American codes cited earlier. Hence, there's a need to be very careful in performing push-on analysis using a mix of Indian and American codes. Now, the problem, what are the issues, what are the difficulties? The difficulty is sometimes the demand curve and the capacity curve do not intersect. Okay, see here, you have carry out this push-on analysis on your building and you get this kind of spectra. You expect you get this kind of spectra where the demand spectra will intersect the capacity spectra. But what if they don't intersect? It's quite common. Okay, the demand spectra, capacity spectra is not necessary that they will intersect. It depends on the properties of your building, depends how you carried out this analysis, how the passages were defined, and so on and so forth. There are large number of parameters which may force these two curves to, fall in their own ways, and they may not intersect at all. Sometimes the target displacement obtained by the two methods, that is EL and DM, give two widely different results. And what do you do in that situation? If they don't intersect, that means, or you get very widely different results, you have to carry out iterations with different input data. Okay, so don't be in the impression that you carry out this push-on analysis, you get beautiful curves and you get target displacement and the matter is over. The matter may not be over. It may run into a lot of serious difficulties. Okay, so that's why I'm saying that you have to be very, very careful while carrying out this non-linear elastic analysis for steel building or RC buildings. Well, that's all I wanted to discuss with you today. Thank you very much. If you want, you can refer some of this information which I discussed from, which is given in this book, which is available by Pearson in 2016, published in 2016. Okay, thank you very much. Now I would like to invite your questions. Somebody asked the question, what is artificial damping? Okay, artificial damping means, see, each material has damping is a function of there are different kinds of dampings. Okay, there are in fact 4 different types of damping. One is called viscous damping, other is structural damping, and friction damping, and I think one more. So most of the time we are using viscous damping, which is a function of the material of the structure, not the structure itself, but the material. So this, when it still has a damping of 2% or 5%, a concrete has damping of 5%, that is called viscous damping. Okay, what we can do is we can apply certain artificial damping into the system. Okay, there are equipment, there are machines which we apply on a structure. Okay, through they're basically hydraulic jacks. They're applied, so the intention is to resist the motion of the earthquake. If the earthquake wants to push the building towards right, the jack will act in the opposite direction towards left. Okay, if the building wants to push the building to the left, the hydraulic jack will apply the force to the right. Okay, this technology is quite popular nowadays. It is well established. Okay, depending upon your requirement, you apply certain artificial damping into the system. Okay, a lot of literature is available. You can just Google it, and you will find, artificial damping, how to impart into it.
What is shear flow? That is the question again.
Shear flow is actually something which is related to torsion in open sections. So shear force, you know what is shear stress? Tau. From the shear force, you can calculate shear stress in any section. Okay. If you multiply this shear stress by width of the section, that is width of the flange or width of the
our code.
Say it again.
Sir, please go to the next question.
No, I'm going to the next section. I'm talking about shear flow. So what I'm saying is shear flow is defined as shear stress times width of the element. That means in a flange, if you calculate the shear flow in the flange, it is shear stress times the thickness of the flange. If you're calculating shear flow in the web, then it is the shear stress in the web times thickness of the web. That's called shear flow. It is important to calculate shear center. Okay. Next question is, our code gives the curves and formula for 5% damping. How do I determine forces with increased damping? See, once you use artificial damping, then you have to carry out time history analysis.
Professor, just I'm interrupting.
Yes, please.
The shear flow, when you are calculating the shear flow, that
Yes.
you'll have to multiply the complete width of the section or half of the width, because shear flow is to a closed curve. So through the wave, one side it will go, other side it will be down. And because of that, when you are calculating the shear flow, half of the width if you multiply, then only it will give the correct shear flow. Am I right?
No, we don't multiply by the width, we multiply by the thickness. T.
Yeah, the thickness of the wave. Yes.
Yes.
That half of the thickness we should multiply, or total complete.
No, thickness is thickness, not B, not the width. Thickness T, small one.
Because the shear flow, it will complete a closed curve.
Agreed.
So in that wave, one side it will go, other side actually it will be down. So if you multiply the complete thickness, it will be twice of that. So if you half of the thickness will multiply.
No. I think you are confusing. See, in a channel section, the shear flow will start from the, let's say, from the top flange, go down to the web and go down to the right. So it's only one way. There's no return path.
Okay.
There's no return path. Okay. Same thing is in the I section. It goes from the to the flange from both sides toward the middle, go down and then go back in the lower flange.
Okay, sir. Thank you, sir.
So it is thickness, not width. It is full thickness T, not T by 2. Okay. Now coming to the next question about this 5% damping and how to determine force with increased damping. The 2002 code gives certain multiplying factors for high dampings. Okay. If they serve your purpose, fine. Otherwise, you have to go for actual calculations using time history analysis of the building during the given earthquake for given damping. Okay. So that will automatically give you the correct results. So there is no formula as such. Okay. You have to carry out the basic analysis using time history of the building due to a given earthquake. Now the next question is how to calculate lateral torsional buckling moment in channel section. Well, the formula are given quite well in our IS codes. Okay, so please refer the IS code. It tells you in different kind of sections how to calculate lateral torsional buckling moment, MCR. Okay, so you please refer it again. IS 800 gives you all the details.
Sir, just one doubt, sir, please, sir.
Yes, most welcome.
Sir, actually, when a section is given a torsion, so that shear flow should be a complete closed one. Hello. So in the wave itself, there will be two flow, one up and one down. Because when we are applying torsion to a section, let it is a I section, some torsion is applied. So the shear flow should be down. It will start here, it will complete a cycle. So I am getting confused whether in the wave itself there is one up and one down, because when you are applying a torsion, in actually what you told actually, like a channel section, when the load is applied, transverse load, that time the shear flow may start from top and end at the bottom. That is there. When the torsion is applied, then shear flow will be a closed one. That time, sir, can you please explain me this point? I'm getting a bit confused.
I think my suggestion is that I understand your point is very valid, but we have to postpone it some other day, because today I didn't discuss shear flow at all. In fact, I didn't even use the word shear flow in my entire presentation. Okay, so my request to you is, let us postpone it for some other day where I can have a full-fledged lecture only on calculation of the shear flow or the shear center.
Yes, sir. Thank you, sir. Thank you so much.
Hello.
Yes, please.
Hello.
Yes, please. Boliye. Go ahead.
Sir, this is regarding the lateral buckling constant for the channel section. In the
Yes.
code, it is only given for prismatic sections, and in annexure, it is given only for sections which are symmetric about minor axis. There are
Yes.
no reference, no formulas given for the section symmetric about major axis. That is the channel section. That's why I asked that question.
Okay. For that, you have to refer. There's very good books on steel structures written by American and Australian authors. So you have to refer those books where they have given experimental results and a lot of equations for those kind of situations which you are talking about.
Sir, so what do you mean?
See, code cannot cover all the situations.
Okay.
Okay. So code only gives you general situations, and if you have a very special situation, obviously you are expected to refer specialist literature, and all the data is available. Okay, so you have to refer some good books on steel structures, not textbook for which we use over our undergraduate and postgraduate studies in our classrooms. No, not those books, but books which are based on totally on research. So they gives you a lot of information, all formulas, all how they carry out the tests, lab tests or analytical tests, and you will find your answers.
Good evening, sir.
Yes,
Good
please.
evening, sir. Sir, you said one point that there is no experimental analysis done in India to estimate the seismic capacity. So what was the problem that we could not do that?
No, there's no problem. Somebody has to do it. See, carrying out a lab, working in the lab is very, very tedious. See, it is very easy to work in a air-conditioned room. You're sitting on your laptop using very beautiful, computer models and so on and so forth. But to go in the lab and developing a fabrication, erection, testing, it's a hell of a job.
Okay, sir, one more question, sir. Like there in AIC provision for residual compressive strength of brace, they consider the 33% of the residual compressive strength. And in European code, they just neglect the residual compressive strength. So is there any provision in Indian code regarding that thing?
See, Indian code, I don't want to talk about Indian code because Indian codes are copied from the European code. IS 800 is totally copied from EC3, and certain information has been removed from there. So let's not talk about those codes. Okay, as far as the 30% is concerned, I carried out testing myself back in 1975-76 in US. I was the first work I did. My work is the pioneer work in the post-buckling strength of axial loaded steel members, the steel braces. And I found that the strength, post-buckling strength of a steel brace subjected to cyclic axial load varies from 30% to 60% depending upon the slenderness ratio. If the L/R is 30, let's say, then the post-buckling strength is 60%. And if the L/R is 120, 150, then the post-buckling strength is 30%, which is not a small strength. So the American code, in fact, your AISC 360, it refers to my research, which is given in the code. Okay, my papers are referred, cited in AISC 360 where they talk about these brace strengths and
Sir,
basic
you-
numbers.
Sir, your research is supported by Rai and Goel, a paper of 2003, where they found 55% of the residual compressive strength.
A lot of people have done that. A lot of people have verified my results, which I did in 76.
Sir,
Okay.
how the braces induce extra axial stresses in columns? Like one place you said, when we include the braces, there will be extra axial stress in the.
See, the thing is, when you take a MR frame, moment resistant frame without any braces, you get very flexible frame, right? And when you introduce braces, you introduce a very slender brace, 150, 180. You will find there's a drastic effect on the lateral stiffness of the frame. So how does this work actually? Okay. So whatever story shear is there, because you apply the same force as you applied in the case of MR frame. Okay. So once you apply the same force, lateral force, then part of the lateral force is carried by the brace. Now, where brace is connected? The brace is connected to the columns only, to the beam column joint. Right? So once this brace is carrying axial force, where that axial force will go? For equilibrium. You take this equilibrium of the beam column brace joint. So if you resolve the force in the brace, they will go vertical and horizontal component. So that brace component will go into the column only.
Yes.
That's why there's an increase in the axial force in the columns. And that's why they say that when you design a column, don't take more than 30% to 40% of its capacity, because during an earthquake, you don't know what is the magnitude of the earthquake. Okay, if the earthquake is very high, okay, then it will generate more axial force in the column, in the base, and that will go again to the column. So if the column carries very high axial force, its moment carrying capacity will reduce. You don't want to make it unsafe in terms of moment capacity.
Sir, there was one more thing, like you said that for 30 slenderness ratio 30, you were getting 60%. But when you say when you see the Vakavyasi paper of 1978, where he studied the where he experimentally studied the diagonal brace frame, there he found when the slenderness ratio was around 26 to 30, it deteriorated the brace frame rather than increasing the strength of the brace frame. Means it was like you explained initially, that when we use a slender brace, it acts as a fuse, and when we reduce the slenderness ratio too much, so in that experiment it was found that the strength was deteriorated. So I was confused that you got 60% for that slenderness ratio of 30.
Now it's okay. Are you clear now? Are you still confused?
Yes, sir. I am confused that the residual strength has increased to 60% rather.
No, because you are using a very slender, very stiff brace. If you're using a very stiff brace, which will not buckle, basically it will go into yielding.
Yes, sir.
So that's why its residual capacity is very high.
Yeah.
And
so
then,
it is.
see, the
so
problem is just a minute. The problem is you have certain ratio of the member sizes for the beams and columns. Now, beam size, column size, and brace size have certain. You have chosen certain proportion, right? Because now it is not just MR frame. You are having beam, column, and brace. All three have certain their own stiffness. That's why it becomes very complicated now. We're talking about three different stiffnesses, and therefore it is possible under certain conditions the whole system may become very bad. That's what you are talking about, that Vakavyasi paper.
Yes, sir. Yes, sir. So it is related to the axial stress induced in the column due to the strong brace.
It all depends on the relative proportions of the beam, column, and brace. You can't have a straightforward single answer.
Yes, sir.
Okay.
Thank you, sir.
Okay, welcome.
Okay, sir, let's go to the next question.
Can BRB brace be used for MRF buildings? Why not? BRB means buckling resistant braces. They are quite common nowadays. They are being used in MR buildings only. See, when you say MR doesn't mean anything now. Once you are using brace, BRB brace, then either you are using a CBF or EBF, mostly CBF. To put eccentrically braced frame, which section or sections are suitable? What do you mean? To put eccentrically braced frame, which section or sections are suitable? I'm not clear about the question. What do you intend to say? Could you please elaborate? This is from Professor Saurabh Kar. Is he around?
So I think you skip to the next one.
In practical applications, capacity design becomes almost impossible. The contractor client or arch will require same size of beam, hence expect hinge to form at. Yeah, you are given the answer yourself. See, if the contractor doesn't want, client doesn't want, or architect doesn't want, what can you do? You have no option. See, they have to agree. You see, the thing is that the architect has to understand why capacity design is important at that particular situation. Similarly, contractor has to be a competent contractor to carry out the work. They can't use their own choices. No. In a given situation, it is the choice, the decision of the structural designer. Or otherwise, he has to tell the architect that find something else, go for some other structural system. Okay. So the architect and the structural engineer have to work together. Architect, see, you can't hire a ordinary architect from anywhere working in some small office, or even in a big office who is not familiar with the requirement of capacity design. The architect has to understand, physically at least, why capacity design is required at a given situation. Okay. If the architect is not competent enough, then you can't do it. Forget about it.
I think, sir, you take the last question, and the rest questions we will email you and get your reply and send it to the senders.
Sir, one question. Sir, can you please highlight some concept of this inelastic buckling?
See, the thing is that, when you keep on increasing the axial force, okay, two things will happen. Either you will have Euler buckling, pi square EI by L square, or the buckling load is such that the yielding will occur first. See, yielding is also there. Metal may yield before buckling. There are two options. Either the member buckles, yielding doesn't take place, yielding comes much later. So yielding is not able to take place because member has already buckled. Second option is that yielding has occurred and member has not buckled. That is possible if the LYR is very small, say 30. If the LYR is 30, quite possible that the member will not get a chance to buckle, and instead, because you are increasing the axial force, it may reach the yield level first. That's called inelastic buckling. Okay.
Sir, anyway, when Euler buckling load will be reached, anyway, when it will get buckle, finally the material will get yield. Because
no, wait a minute. Once Euler buckling occurs before the stress level reaches yield stress, then yield stress will never reach. It has already buckled in matter of.
Now, when they will start, actually, when the Euler buckling load reached, when it will start, that time
there is no time. There is no time gap. It buckles suddenly. You don't with the blink of eye, the member buckles. Finish. Go on. I have seen the buckling myself. You blink your eyes and members buckle. There is no question of further going into the yield level. Yielding is
so that is, sir, actually, but all practical cases, there must be some eccentricity.
Yeah, sure. Why not?
In the member, yeah.
Yes.
So that time, actually there is no case of Euler buckling.
No, 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 that's not true. See, eccentricity is always there in real buildings.
Yes, sir. When the member will be subjected to axial load, that time, if there must be some eccentricity, in that case, the inelastic buckling concept, if you something you can tell, because actually the concern is how the stress variation along the thickness of the member. This, so that way actually, sir, can you please?
I think let's do it some other time, okay?
Okay.
What is the last question you mentioned?
Sir, you select one last question because we are already out of time. So one suitable one which needs attention.
I think I've already answered most of the questions that they are already there. And it says, how can I want to be master in non-analysis? Well, you have to study the subject under a qualified person. Okay. So it's a very good question, no doubt about that. But you have to do a lot of reading, a lot of Excel sheets. Okay, you have to work on Excel sheets. Or you can develop a program in MATLAB to carry out to study the nonlinear behavior. Okay.
Okay,
So
sir. Sir, let us now end this question and answer session because it has been a long journey for you also. So in fact, the topic is still quite complicated, and perhaps in the later stage, we might try to repeat this one.
Sure, sure. I
This can be
understand
done,
that.
but we are fortunate that you will be taking 2 more classes on the codal provision, which might also give a little bit of sight on this topic. So I would like to thank Professor Dr. Jain and also the participants, and would remind the participants that our next session, which is on 23rd June, is on another topic, understanding wind load. This today was the earthquake load, next day is the wind load, which is to be delivered by Dr. Professor Prem Krishna and Dr. I just don't recall the name at this moment.
I think
Might be. So that is on 23rd of June. We will be sending you the brochure today itself, and kindly register, which will be also from 3 p.m. on 23rd of June. With this, sir, I thank you very much. And we will be meeting with you again in July for 2 sessions on IS 1893. And also thank the participants for joining this program. Thank you very much from INSDAG side.
thank you. Thank you. All the best.
Thank you.
Thank you.
Thank you, sir. Thank you.
Thank you, sir.